Hey there, and welcome. You ever just stop and look around at, well, everything, and wonder how it all gets made? I mean, the steel holding up our buildings, the phone in your hand. How does it all come to be? Well, today, we're going to dig into the blueprint of progress. We're talking about the science, the engineering, and the brilliant people who build our modern world, literally from the ground up.
So yeah, how does it all happen? How do we go from, say, a chunk of rock in the ground to a massive skyscraper? Or from a basic on-off switch to a factory that pretty much runs itself? That's the huge question we're going to tackle, and we'll follow that incredible journey where science and tech really come together to make it all work.
All right, here's our game plan. First, we'll start with the basics, the ultimate toolkit of science. Then we'll see how we use that to master matter and energy. After that, we'll look at how all of that scales up to build our public infrastructure. Then we get to the cool part, adding a layer of intelligence with automation. And finally, we'll talk about the amazing professionals who make every single step possible.
Okay, first up, Section 1, Science, the ultimate toolkit. You see, before you can build a single thing, you need a shared set of rules, a common ground. This is basically the universal language that all engineers have to speak.
And that shared language? It's called engineering sciences. The best way to think of it is as this super important bridge. On one side, you have pure scientific theory, and on the other, you have real-world, hands-on applications. It's not just about knowing the science. It's about knowing how to use it to fix things and solve really complex problems.
The thing is, engineering sciences isn't just one subject. Nope, it's a powerful fusion of a whole bunch of them. It pulls from the hard physics and chemistry that run our universe, it uses math to model everything, and then it mixes in specialized fields like materials science and fluid dynamics. It's all about creating one unified, powerful toolkit.
So now that we have our toolkit, let's move on to Section 2. How do we actually use these tools to harness the most fundamental building blocks of our civilization? We're talking raw materials and pure, unadulterated energy.
You know, it all starts with getting the right stuff to build with, and this is the domain of metallurgical engineering. These are the folks who manage the entire journey of a metal, from digging it out of the ground as ore, all the way to turning it into the high-strength steel or the super-light aluminum we use in, well, everything.
So, how in the world do you get a pure metal from a rock? Well, there are three main ways. You can use crazy high heat, that's pyrometallurgy, for things like steel. Or you can use chemical solutions to dissolve and pull out metals like gold, that's hydrometallurgy. Or you can use powerful electric currents, which is electrometallurgy, to get super pure aluminum. Pretty wild, right?
Okay, so we've got our materials. Now, the million-dollar question, how do we make sure they won't, break? That's where structural mechanics comes into play. It's the science of figuring out how a structure, whether it's a bridge or an airplane wing, is going to react when you push and pull on it so we can make sure it doesn't fail.
Now, there are two really critical ideas here: stress and deformation. Picture this: you're stretching a rubber band. The force you're using to pull it creates stress inside the material. And how much the band actually stretches, that's the deformation. Engineers have to be masters of this relationship to design everything from skyscrapers to paper clips, making sure things can bend a little without ever breaking.
But look, making strong stuff is only half the battle. We also need to power our world. And that brings us to energy and the science that governs it all: thermodynamics. This is the absolute core principle behind every single engine, power plant, and even the refrigerator in your kitchen.
Thermodynamics is ruled by 4 laws you just can't break. They cover everything from how we define temperature to the fact that energy can't be created or destroyed. But the most famous one has to be the second law. It basically says that disorder, or entropy, always increases. It's the reason your hot coffee gets cold. It's why no machine is ever 100% efficient. This one rule sets the limits for every engine we could ever hope to build.
All right, let's jump into Section 3, Building Our Modern World. It's time to take those fundamental ideas about materials and energy and see how we apply them on a massive scale, to create the very infrastructure that we all depend on every single day.
Public works. This is the true backbone of our society. We're talking about everything: the roads and bridges we drive on, the dams and water treatment plants that give us clean water, the power grids that light up our homes, and the ports and canals that connect us to the rest of the world. It's huge.
Let's just zoom in on one of those areas, hydraulics, to see how deep this stuff goes. I mean, think about it. From the clean water that comes out of your faucet to the massive power generated by a dam, managing water is absolutely essential.
Urban hydraulics keeps our cities running, agricultural hydraulics grows our food, and industrial hydraulics powers heavy machinery. It's a perfect example of one single field that has a massive impact on all of our lives every single day.
And now for Section 4, the rise of automation. So our world is strong, it's powered up, but now we need to make it smart. This is all about creating a sort of digital nervous system to control all the complicated machinery we've built.
You know, the idea of making things run by themselves is not new at all. It actually goes all the way back to ancient Greece. But this timeline shows the real game changers, from James Watt's mechanical governor that tamed the steam engine to the invention of the PLC, the Programmable Logic Controller, which basically made modern factories possible, all the way up to today's Industry 4.0, where factories are becoming truly smart. So, what is automation really? At its heart, it's the science of making systems do what you want them to do all by themselves. The key phrase there is without direct human intervention. It's about setting the rules of the game and then letting the system regulate itself to stay on track.
And there are really two main ways to do this. You've got an open-loop system, which just follows a command and that's it, like a fan that just runs at one speed. But a closed-loop system, that's where things get smart. It uses a sensor to get feedback, like a thermostat checking the room temperature, so it can constantly adjust what it's doing. That feedback loop is the secret sauce to all modern automation.
But let's be real. These incredible systems, they don't just build themselves. And that brings us to our final, and honestly, the most important piece of the puzzle, the people. In this last section, we're going to look at the professionals behind all this progress and what it really means to build the world we live in. We tend to use words like task, job, and profession almost interchangeably, but they're not the same thing at all. They actually show a clear progression. A task is just one specific duty. A job is a collection of those tasks. But a profession? That's something else entirely. It's a career path built on a foundation of deep, specialized knowledge and a commitment that goes way beyond just getting a paycheck.
So what really takes a job and turns it into a profession? It's not just about being good at the technical stuff. It's about committing to a code of ethics. It's about having a responsibility to society. It's about understanding that you have to keep learning your entire life. A profession is when your work becomes a core part of who you are, governed by standards that are there to protect all of us.
And a huge part of that professional responsibility is safety. This is not some afterthought, it's a fundamental pillar. It means everything from spotting risks and preventing accidents before they happen to safely managing hazardous materials and making sure that every single worker is safe and healthy in the long run.
And all of this brings us to one final thought. We've gone from metallurgy all the way to AI, following this incredible blueprint of progress. But as technology keeps moving faster and faster, it's creating brand new challenges around things like sustainability and artificial intelligence. So the question we're left with is this: what new professions are going to emerge to build the world of tomorrow?